Okay, so we're looking at double displacement reactions here for our last, this is actually our last lesson in this unit. This unit is very short. It's really only one chapter kind of worth of material. So double displacement reactions is very similar to single displacement. It's also known as double replacement. The only difference is really you have two compounds that you have on the reactant side. Whereas single displacement, you have one element with a compound. You now have two compounds. So the same general premises happens. So a metal can only replace another metal. A non-metal can only replace another non-metal. Okay, so the difference here though is we will always have the swap out happening. So if you remember for in single displacement reactions, what happened is we checked our activity series for metals or for halogens to see if the reaction would occur. But in this case, the reaction will always do the swap. So, and we've already mentioned this. So a metal can only replace a metal, a non-metal with another non-metal. Okay, so here are a couple of examples. So we have sodium chloride and silver fluoride. What happens is the sodium and silver will swap. So sodium is now with fluorine and silver is now with chlorine. So if you were to imagine, it's like you have two groups of friends and then you have one friend swapping for another friend. Okay, so here we have lead to nitrate plus potassium iodide. So what's happening here, right, is we have the lead is now going to be with iodine and nitrate is now going to be with potassium. So remember when you're doing this, you don't take this and just copy it over here. You have to do the crisscross rule each time you do a new molecule. So that's the biggest mistake I see. So people will go, students will say, oh, okay, lead to nitrate. So that must mean that when nitrate is on this side, it must be exactly the same. So NO3 with the 2. Just because the 2 is here on this side, it's because of the lead crossing down. Potassium is positive 1, so it will not have the 2. So remember, every time you do a molecule, it's like you're doing it for the first time on its own. Okay, so let's talk about this next piece. So when we're looking at single and double displacement reactions, we're going to come across, and we've already seen it actually already a bunch, the term solutions. So the fact that we have a solution, it's important to know what we mean when we say that. So this goes back to basically talking about mixtures. So a solution is a homogeneous mixture, which means that it's seen as one phase, right? We can't see the difference in what is dissolved in there, right? You can see here. And we have two parts to it. We have the solute and the solvent. So the solute is what is being dissolved into our liquid, as it were. So solution doesn't always have to have a liquid, but when we're talking about single and double displacement reactions, typically we are going to be referring to liquid solvents. So the solvent is the liquid component of this solution. So for example, if I had salt and I was dissolving it into water, right, my solute would be the salt and my water would be the solvent. And once the two are together, that makes a solution, right? So homogeneous, like we mentioned, means you have one phase. The solute is the substance that is dissolving. The solvent is what the solute is dissolving into, right? So here we have 100 grams of water as our solvent, 10 grams of whatever you'd like this to be, let's say Kool-Aid powder, right? You dissolve it, and now we have one homogeneous mixture. It all's completely dissolved, and we have a solution. So when we talk about solutions, we have two types of terms. We have something called high solubility and low solubility. So high solubility essentially means that the solution was easy to dissolve or very dissolvable, right? So let's say Kool-Aid powder and water has high solubility. So it's very easy to dissolve and mix. Something that has low solubility essentially is something that cannot dissolve. Or it basically does dissolve, but in very, very, very small amounts. So I would say, for example, oil and vinegar would have low solubility with each other, right? So they don't really mix very well. So these terms are going to come up. So when we say the term solubility, as we saw there with high solubility, low solubility, solubility is essentially talking about how much solute are you able to dissolve into a solvent. The maximum amount that you're able to dissolve will essentially indicate its solubility. So if you're able to dissolve a lot of a substance, we say that that has high solubility. If you're able to dissolve a small amount of a substance, that's known as low solubility. Now, there's a few things that it depends on, and the most important thing here that will affect us will be temperature. However, when we're talking about solutions, most of the time we're talking about room temperature. So when we say something has high solubility at room temperature, we're going to use the subscript AQ. So meaning we are saying that that substance dissolves in water. So if I have salt and it's dissolved in water, I can use the little AQ to indicate that we have a solution. Now, if I have something that is not dissolved in water, so let's say I had sodium chloride that was not dissolved in water, I would not be using the AQ, right? So this is a solution. This would be like the crystals of salt before I dissolve it. So anytime you see the term AQ, essentially what that means is we have something with high solubility, right? So it's dissolved in water. So why is this becoming important when we're looking at these types of reactions? Well, when we're looking at solutions that are doing chemical reactions, we have to have a way of knowing, is this going to be something that is soluble or is this something that is not soluble? So how we're going to tell that is from something called the solubility table. And actually you have this on your data sheet. It's right here. Solubilities of ionic compounds at SATP. It's exactly the same as this one we have here that we're going to look at. So let's talk about how this is organized. So we have essentially a table with columns and with rows. There's 2 rows and a bunch of columns. So I want you to notice that this says solubility of ionic compounds at SATP. In other words, room temperature and room pressure. So that stands for standard ambient temperature and pressure, which in other words is room temperature. So here, the 2 columns essentially separate high solubility from low solubility. So high solubility, you're going to see that there's a little AQ written beside it. Low solubility, there's a little S. So anytime we're talking about a substance with high solubility, we're going to put an AQ subscript beside it when we're doing chemical reactions. If we're doing a substance that has low solubility, according to this table, we're going to put a little subscript S. So this is like how we're going to know more states of matter. Okay, so let's talk about how this works. So each column, at the top of the column, has negatively charged ions, right? So here we have some halogens, sulfur, hydroxides, sulfates, etc. In the rows, you have positive ions, or sometimes you'll see things that say most, or all, none. So what that means is when you're looking at a molecule, you have to essentially look at the column for the negative ion you're referring to, and then check to see where the positive ion lies. So for example, let's say we were looking at calcium sulfide, right? So we'd make sure we're looking in the sulfur column, okay? So we don't care about any other column because we're dealing with sulfur. And I would check to see, well, does calcium fall under the top row or the bottom row? So calcium is in group 2. So what that means is now I'm in this top row. So that indicates that I have high solubility. So whenever I'm writing out CAS in a chemical reaction, I'm going to put the AQ symbol. So let's try another one. So let's say we had lead to bromide. So now that we're looking in the bromine, we have to look in the different column that fits with what we're doing. So bromine is here, and actually I know it's not shown, but fluorine is also here. This is like the halogens column. So we're looking at this column right here. So now I'm going to look to see, well, where does lead 2 fall under? So I can actually see lead 2 is listed right here. So what that means is it has low solubility. So lead 2 bromide, when I'm writing this out, when I'm doing a chemical reaction with this, I would write it as a solid. So we have a subscript of the state of matter that it's in. So this chart actually is a huge help for when you're writing out chemical reactions and you need the states, because it's going to tell you, do you have a substance of high solubility or low solubility? Now be careful. Lead 2 is in this bottom row, but lead, if this was lead 4, lead 4 is not in this bottom row. So what that means is, see how it says most up here? That means everything that is not in this bottom row where it's listing out the ions, every other ion would fall under this top row. So that means lead 4 bromide would be AQ because it would have high solubility. So when you have these ions, be careful. It has to be the specific ion. So if I'm talking about copper, notice this is copper 1. I believe it is. Did I cut that off? Yeah, so copper 1. But that means copper 2 would be up here. So it's important that you have the correct ion that you are looking at. Okay? So if the product in the reaction is soluble, it will stay in the solution and we will put an AQ, right? So that means that we have high solubility, right? But if the product is slightly soluble or not soluble at all, what we're going to do is give it the subscript S, which means that we are going to be able to see the precipitate. It is no longer dissolved in the solution. It has low solubility. So if we have a gas, that's a different story. So this chart here does not tell us if something is a gas or not. This essentially is high or low solubility. However, some of the gases we already went over that you should know. But if you're doing a double displacement reaction, you would see the evidence of a gas by seeing the gas bubbles. So of course you'd have a gaseous product.